got the hardcore photonics community here at the end of the day. So, all right. So, yeah, so I thought I saw microwaves and photonics and a few other things in the title. So, picked the subject that a couple of us who are here, Alex is probably going to connect with this tomorrow a little bit too, but I thought I'd talk about microcombs. And there's been a lot of interest in the last couple of years in using microcombs to generate very stable microwaves. So it seemed like it fit into the theme of the workshop. And again, in the spirit of kind of making this more or less tutorial, but it might be review for quite a few people. Thought I'd just kind of go over the basics of how we're making microcombs, how most groups are making microcombs today, which is using high-Q whispering gallery resonators. What are the key features of those resonators that are important? And then talk about some of the systems. Okay, you've heard about some of them today, like thin film lithium niobate, but one we're focusing in a lot now is called ultra low loss nitride. And I'll show you how we mode lock, okay, using that material. Show you some of the interesting features that it provides because of the fact that it's foundry produced and there's a lot of control that we have available to manipulate dispersion, and show you some of the interesting things that can be accomplished with that material. And then finally at the end talk about the essentially optical frequency division, a specific implementation of it that's being used today to generate really high performance microwaves. These are now, they're at the point right now in microcombs where they're competitive with the very, very best microwave oscillators, which are sapphire oscillators. But combs in general make the best microwaves, okay, by far, okay, it's not even close, okay, anymore in terms of the kinds of stability phase noise levels that are possible. So, all right, so title this first part, Beginnings, and just kind of move very quickly through some of the physics of high-Q resonators, bringing us to the point where we understand how microcombs work, how they mode lock. And so this is, I always like to go back in time, and because it's kind of fun to look at how far the field has evolved in just 2 decades, a little over 2 decades. But 20 years ago, this was everything that was available that could access what we now call ultra high Q. And so there were these spheres, microtoroids, crystalline resonators. If you're not familiar with whispering gallery resonators, they guide light by quasi-total internal reflection. So there's a little green orbit in the lower left, which is literally that sphere was doped with erbium, and so that's excited state absorption. So that's really tracing out what the ring orbit is doing of the light field inside. And the other structures, in fact, every structure today guides light in these sort of orbital motion. They're not always circles. They sometimes are racetracks or sometimes spirals, but generally the idea is the same. And to make the Q very high, loss of the material is low. So you pick good low loss materials, and you also find tricks to make the interfaces, the dielectric interfaces, very smooth. And so in those days, these tricks, gave Qs, that were quite high, 100 million, even 100 billion. And but you can see any of those 3 devices are not integrated, meaning that they do not have waveguides that are on a chip. And so there were special techniques that were also required to couple light into and out of the resonators. And so tapers and prisms were used. And so these were really laboratory devices. Just a couple of other little background, kind of in the spirit of tutorial. If you look at the whispering gallery resonators, I've painted in a little waveguide there that's meant to be a fiber taper. But the idea, again, is we have a resonance condition. And so there'll be an integer number of wavelengths that will be packed in around the periphery. And every time you do that, there's a resonant frequency. And the Q will make the line width of those resonances narrower. So you can see kind of typical line widths, lifetimes, ring down lifetimes, like cavity lifetimes for Qs, a range of 100 million. And then the free spectral range, the spectral distance between the resonances, kind of range of sizes that are fairly typical for these resonators, giving you, microwave rate to even millimeter wave rate, free spectral range values. And then importance of the Q, is that if we envision now coupling some light from a, say, tunable single frequency laser on that waveguide, and if it's non-resonant, then essentially a little bit of light will couple in. And if it's resonant, then essentially there can be a large resonant buildup. And because of the small size and the high Q, finesse is very high. And so the resonant buildup factor leads to huge, circulating intensities for very small couple powers. So a milliwatt in and a toroid like that will be over a gigawatt per square centimeter. And that is actually, in terms of absolute power, even a kilowatt, over a kilowatt of power, CW. So it's really quite impressive what you can do, if the size is small and the Q is high enough. But then what I like to point out, and this is what I think has really driven the interest in this subject and trying to perfect platforms that, meaning like, materials that are now available readily from foundries, but feature very, very low loss levels, is the fact that Q is, like I like to say, quadratically important. And so there's a couple of ways that Q figures quadratically into performance in a lot of devices that are used today. And one of the key ways has to do with turn-on power, threshold. And so there are several different nonlinear oscillators that are used. The one I'll talk about today is a microcomb. And the power level needed to overcome round-trip loss, meaning the gain equal loss condition, the threshold condition, varies inverse square with Q. It scales like the mode volume divided by the Q squared. And one of the Qs is coming from that resonant buildup effect that I just spoke about, and the other Q is coming from the fact that the loss, of course, the round-trip loss will be lower if the Q is higher, so it doesn't necessarily have as much nonlinear gain. And so turn-on powers, you can see in a couple of these early devices, a little microsphere Raman laser, third-order parametric oscillator, using the Kerry effect, less than a milliwatt, just because of this nice high Q property. And today, what we like to do, we like to try to target devices that can turn on with power levels that are low enough to be readily accessible with 3.5 lasers. And so that heterogeneous integration of the lasers, for example, makes it easy to turn them on, but also have enough margin left over so that something useful, can be done with the oscillator. And so, and along those lines, this threshold for the third-order parametric oscillator, it's the same threshold that we have in the Kerry combs, in the little soliton microcombs that are now finding lots of different applications. So again, this is I think one of the key reasons there's been so much interest in driving up Q. The other that I'll come back to very, very briefly, and we could spend the whole hour on this subject alone, but is the frequency noise of these oscillators. And so that has a short-term and a long-term component. The short-term, which is white frequency noise, scales. It has like a kind of a shallow Towns-like behavior, if you're familiar with the shallow Towns line width formula. And so the Q, again, will drive down white frequency noise in an oscillator, like a laser oscillator, very, very quickly. It'll take it down quadratically. And so this is another good reason to have a very high Q. All right, mode locking, just some quick background on that, how it works in whispering gallery resonators. So again, if we have single resonance, I've just talked about that, and there's some things we can do, but mode locking involves many resonances. And the idea is to fill these modes with energy, but then also find a mechanism that will phase lock them. And so that it's possible to have a periodic pulse train. Pulse train could have any form. It could be a square wave or some other irregular shape. In fact, there's lots of combs today that operate in this kind of other non-femtosecond regime. But what I'm showing here is a case where we're trying to align the phases to create very, very short pulses. So this would be kind of the typical way we envision mode locking unfolding. And so the pulse width is going to vary like, the spectral width, of inverse with the spectral width of the number of or the modes that are locked. And then the 1 over the free spectral range, or just the round trip time of these pulses around the cavity, will then give us the separation, in the pulse stream. And so kind of now coming, somewhat more forward in time. So the device I'll be spending a lot of time talking about today, the soliton microcomb, it's basically the mode locking mechanism. We have these modes in there. The mode locking mechanism is the formation of soliton pulses. And there's a very well worked out equation of motion called Bugiato-Lefebvre equation. I left out the charts on that today. But if you're interested, there's a nice review here. I've listed in a little box, and it goes into some detail. I can give you references. But essentially, those pulses form, and the physics of their pulse formation is very similar to the physics of the way pulses or the soliton pulses have formed and been studied in optical fiber, for many, many decades. And you need a quadratic dispersion, okay, anomalous dispersion, and that has to do with the sign of the Kerr effect. And if you can arrange for this to happen, then it's possible to actually form these pulses, and they will propagate. Now the energy, okay, the mechanism that's driving the system is actually the coherent gain, okay, provided by the Kerr effect that I just talked about just a few charts ago. And so it's kind of interesting about the microcombs, the Kerr combs, as they're sometimes called, is that they not only mode lock by formation of solitons, but they also come with their own built-in gain. And so it isn't necessary to dope the material. You could dope this with erbium, for example, and you could try to amplify using the erbium ions in the silica. This is a silica with spring gallium resonator, but it isn't necessary to do that. So essentially, you just put on the material. You try to make it as pure as possible. It could be nitride, silica, many other materials. And this process will work to actually amplify and overcome the round trip losses of the solitons as they propagate around. And so kind of quickly reviewed some of the key landmark points in the history of these little devices. But the microcombs, modern microcombs that we use a lot now, they really burst on the scene 10 years ago. In fact, it was just almost exactly 10 years ago. And first in mag fluoride, and then quickly in some of the other dielectrics. Some of the early spectra are being shown in the right. And you can see the little peak at the top of those spectrums. Those spectra, that is the pump, okay, that's coming in, is actually providing the gain. And then there's a hyperbolic secant squared envelope, okay, that these combs obey. And this is all predicted, okay, from this Bugiato-Lefebvre equation, solutions to that equation. One other interesting feature that I'll talk about a lot today, in that lower right spectrum, this was on a silicon nitride comb, and that comb actually features a little peak at the low frequency end. You can see it kind of coming up. It's physically not part of the soliton. It's something called a dispersive wave, very well understood in optical fibers, but these waves are essentially features that can be engineered into the spectrum, and they represent places, sometimes mode crossing, sometimes places where the soliton is accidentally even re-encountering the mode family that it's using to form. And but they allow the soliton to throw coherent power, okay, into spectral regions that are typically where the comb power from the soliton itself is very weak. And so you can kind of see why that would be useful. If you want to actually have spectral extent and access coherence further away from the pump, and these dispersive waves are very, very useful. And you'll see how useful in just a little while. All right, so that's just some real quick background on soliton microcombs. And so now I want to talk about real quickly, there's a lot of different dielectric materials that are being studied now, but these are certainly three that are very prominent. If you look through the literature, and I'm speaking to the choir a little bit because I know that Stanford, there's a lot of work on thin film lithium niobate. We heard about it earlier today. But foundry-based materials are now available with very, very low loss levels. Let's begin with thin film lithium niobate, which came to get into existence just in the last decade. But it's essentially has all of the nice features of lithium niobate, workhorse material communications, strong second-order nonlinearity, electro-optic modulation. But now you're combining that with the ability to lithographically define waveguides and resonators, and dispersion engineer, okay, and do a lot of really powerful new functions, okay, that magnify, okay, the properties of lithium niobate. So it's a great new material. and a lot of amazing new devices, okay, coming out of that material. One on the far left is one. It goes by the name, sometimes called high confinement silicon nitride. It was really the first version of silicon nitride that really punched into this very, very high Q limit, and has some really impressive Q numbers. It also features anomalous dispersion. Okay, so it was the first nitride material to produce, the solitons, these little, as we sometimes call bright solitons. And that's because the thickness of the nitride actually naturally leads to anomalous dispersion. Now, material that we study a lot, other groups are also beginning to study this, is in the middle. It's this ultra low loss silicon nitride. It's there's nothing mysterious about this material. Okay, in some way, it's a logical extension of high confinement nitride. It's produced in foundries, and the idea here is to make the nitride thin. And you make the nitride thin enough. In this case, typically somewhere between 50 nanometers and 100 nanometers. What happens is that the loss of the wave becomes more determined by the silica, okay, the cladding material rather than the nitride. The Q goes up a lot, and so you have these really tremendously high Q values, approaching even now almost 1 billion, and the waveguide losses are equally impressive. And so if you think about properties that determine device performance, so short-term frequency or frequency noise, turn-on power, this looks like a really intriguing material. But it has one downside, and the downside that I'll come back to is that it has normal dispersion. So it has been difficult until quite recently to make femtosecond pulses in it. I have one chart, okay, debated, I knew I would run out of time if I put too many charts in, but this is one chart on noise, okay? And I just wanted to show some of the things that are possible now because of this new material. And this is a kind of a device that operates by self-injection locking. And it's a 3.5, you'll see the little photograph right there. It's a 3.5 laser that is self-injection locking to what's called a high Q spiral resonator. And this uses this special nitride material. There's actually 4 of these resonators there. They're interleaved Archimedean spirals. The Qs are quite high, and that quadratically lowers the white noise, the white frequency noise of the system. And so you end up with a short-term noise improvement. The reason that we're using the spiral in this case is that the length of the spiral, which in this case is over 1 meter, also does something else. It averages down another source of noise, which occurs on a longer time scale, and that's called thermorefractive noise. And so the combination of the spiral operating in this self-injection locking manner is to produce a device that has short-term, long-term noise, frequency noise improvement. And it's really dramatic how well it works. So in the lower right, the black curve is a frequency noise spectral density function data taken on a high-performance fiber laser. In fact, we took this data together with the engineers at the company, the fiber laser company. And then the blue data is actually one of these little, we call them spiral sills. And you can see that, all the way down to an offset frequency of 10 hertz. Okay, it's just fairly long-term noise components in the frequency noise. This little spiral sill is working really well. It's competing very favorably with the fiber laser. And so that's the first time that a diode laser like this, modified just a little bit, has been able to actually do this. Fiber lasers usually are orders of magnitude better, especially on the low offset, region of the spectrum, compared to 3.5 lasers. One other significant new development is that John Bauer's group has now got these fully heterogeneously integrated. Just about 2 months ago, I've seen these little dies, and so these things, they literally can be stamped out, okay, in parallel and put into little butterfly packages. And so that might be something, that starts to be commercially available in the coming years. All right, so that's coherence. I want to come back to the mode locking. And so I mentioned that the low loss nitride has this problem. It has normal dispersion. And a couple of comments on that. We have found a way, okay, to actually sort of very readily, deal with the normal dispersion. And this is the way we're dealing with it. There certainly are other possibilities, but the idea is to couple 2 cavities together, this cavity A and cavity B. This coupling, there's a time domain and a frequency domain sort of explanation for this. I'll show how they both work. But the time domain, what happens is that this device mode locks, and it mode locks readily. This is not difficult to do, but it mode locks and forms femtosecond pulses by actually forming pulse pairs that are coherent with each other. And so you can see this blue and this red pulse. And what happens is that most of the time, those little pulses are propagating in normal dispersion, and they're broadening just a little bit in time, very, very small amount. But as they enter that region, the blue and the red pulse couple and recompress. And so that compression then in a round trip sense leads to the stable, on average pulse. It's not a true soliton. It's only it's a femtosecond pulse in the kind of the round trip sense, but it still creates very, very nice broad spectra. You can see typical spectra in the lower left. There's a blue and a red corresponding to, the through port is the cavity A soliton, and the drop port is the cavity B soliton. And they're slightly different, in spectra, even though, they are coherent. Now that's the time domain. The frequency domain version of this is also kind of easy to understand. Once you realize that what we've done in forming these two cavities is that the round trip on each of the cavities is slightly different. And so the free spectral range is very slightly shifted from cavity A to cavity B. It's 100 megahertz difference on a nominal free spectral range of 20 gigahertz in this case. And so if you think about that, what that means is that if we scan the frequency of a tunable laser through the system, then we'll see periodic recurrences where the cavities will be nearly degenerate. You'll find modes that are close together. When this happens, then there's a mode hybridization, and the hybridization leads to a strong avoided mode crossing. And then as you tune away from that, the hybridization slowly weakens. And so what we wanted to do here was to create a kind of a slow drifting in and out, if you will, across the spectrum of this strong to weak hybridization. And what that does, you can see in the right panel, the mode number 0 there is actually just an arbitrary number. It's around 15, 60 nanometers. But there's an opening up, a gap, that's created. And the two lines, the red and the blue that are crossing each other, it's a way of actually representing the dispersion of the cavities independently, without any coupling. And at mu0, we've actually knocked out a linear dispersion term. So we're seeing just the second order and higher dispersion. Yeah, Amir. Yeah, we can shift them, and I'll show you how we can do that a little later. We actually put tuners, on each of the cavities now. Either PZT or thermal tuners. But yeah, it'll generally be at a, kind of, as you would imagine, kind of a random location depending upon the fabrication, right? All right. So now, so you can understand, I guess, kind of coming back to this, you can kind of understand the frequency domain curvature up. By the way, the green is our measurements. So the green are measurements, and the other points, which are kind of in the background, are the model. But through this kind of hybridization that happens, there's a cusp, sort of an upward curvature, and it's at that point where we have anomalous dispersion. So we've induced anomalous dispersion, and you should be able to create solitons there. And that's sort of the frequency domain picture of how this mode locking actually occurs. Now, I want to make one other comment, though, because I don't want to make it seem like it isn't interesting to have normal dispersion. And this is, I think, something, I think Alex will pick up on this tomorrow, probably in his talk. But there are a lot of interesting combs that you can form from normal dispersion. And these are non-solitonic. They're essentially, it's mode locking, still works the same way, but essentially the pulse shape, is not the kind of classic soliton shape. In fact, it can have various different, waveforms. These turn out to be really useful, for different reasons. In fact, I'll show you, we use these in some of our work, but they are much more efficient combs. And so you can produce much more power per line with these combs. Although the spectral extent in playing some of these games with the dispersive waves that I'll come back to, it's easier to do that, with the bright combs. But I just wanted to point this out. And also this idea of using coupled resonators, to actually, play games with this type of comb. This is something that has also been around for a while. And so this coupling of resonators is not a new trick. It's just that we're sort of implementing it and doing some different things with it now in our work. Okay, so now I want to come in and just sort of talk about a few other really interesting things that happen in this coupled system. So one other feature as a result of the partial coupling is that actually these windows where you have anomalous dispersion and where it's possible to form pulses are recurring. And if you think about it, that's quite reasonable, because if there's a difference in the FSR between the two resonators, they will sort of experience a kind of a moire effect, right? There's a vernier effect. And so they'll come in and out of resonance. And as this happens, you'll periodically open up gaps. And so you would expect to see multiple anomalous dispersion windows. And in fact, you'll see these in kind of the symmetric and the antisymmetric hybridization bands. And so this plot on the lower right, this is data, the green is data, where we've actually mapped out this dispersion. And you can see this upper band, which is the antisymmetric band, and then the symmetric band below. And there are multiple places where one would expect to form solitons. And so, for example, that lower band, okay, if you shift over and change the frequency a little bit, it should be possible to generate solitons there. So one thing we wanted to do is to check this. In fact, this does work. And so here you see, we're pumping on the two different bands, and you can form these nice solitons in each of those bands simultaneously. They also are very coherent, as evidenced by detecting the beat node. And so in the upper right, you see the 1550 pumping and a 1582 pumping. That's giving us these two different soliton spectra, and they're producing these very, very nice narrow beat notes on the spectrum. You can also run it in opposite directions. Okay, this is not really that surprising, but you can basically populate and put solitons at different places. We've now taken this another step. I didn't incorporate this data today, but we can do this over a wide range of wavelengths. And so we have these running at 1 micron, at 780 nanometers, and we even have produced the curvature, although we can't pump them effectively yet, all the way down in the green, okay, at 532. And so you really can move these windows around readily to produce solitons, in places where it would almost be impossible to form solitons normally because of the very strong rise in normal dispersion. All right, so that's pulse pair mode locking. I want to go through real quickly some interesting things that result, okay, from the combination of, having this coupling, this precise control, and also kind of coming back to Amir's question, tuning. Okay, what happens when you tune these systems? What new features happen? And one of them is shown here. And this actually kind of directly answers your question, Amir, is that if the idea on this plot, cavity A and cavity B, is that each line is representing a frequency of the cavity. The FSRs are different. And so you see in the overlay, there is this kind of moire pattern, okay, that happens. And so where the moire pattern is very light, this is where there's strong hybridization. Where it goes dark, you're interleaving the resonances, the hybridization is very weak. And so it's coming and going as we sweep along. All right, so now everybody's seen moire patterns before. And the other thing I'm sure that everybody's done at one point in their life is that if you take moire patterns and you slide them like this, then there's this effect literally called the moire speed up effect. And the moire speed up effect means that a shifting of one of the patterns by just a very small amount will be magnified in this sort of interference that you see. And so the idea here is that we can use that in these coupled ring systems to sort of introduce two kinds of tuning. We can have common mode tuning of the cavities, in which case the FSRs shift together. The moire speed up does not happen. The other thing that's possible is we could differentially tune the resonators, in which case then you see this extremely rapid change in the interference or the overlay. And what that means is that the dispersion is now being tuned very rapidly. And so, to answer your question, by differentially tuning, we can literally move the dispersion around a lot. And so this is the implementation in the lower right. I put that little photograph there because I did want to make one other comment about it. But you can see the little wires coming over. They're going over these little heaters. And the pads for the heaters are what you see. The heaters themselves are almost invisible. They actually wrap around, okay, the nitride. And The laser itself is directly pumping the comb. In this case, it's just end fire coupled. And it's kind of significant for two reasons. One is that we can directly run this comb from that DFB laser. And part of the reason we can do this is because the Q is high. This is a large mode volume resonator. It operates at what in the microcomb world is considered a low repetition rate. It's around 20 gigahertz. And so there's a big mode volume. It takes a lot of power to drive it. The Q has to be high enough to overcome that mode volume. And so that's one reason we can do this. But the other notable thing is there's no optical isolator here. So this system is also self-injection locking. And there's a whole interesting story here that kind of unfolded over a period of 3 to 4 years. The story ended about 3 years ago. But this is this self-injection locking mode for these lasers, for these combs, not only cleans up the comb coherence, but it also makes the turn-on properties very, very straightforward. And you literally turn on the laser and the comb turns on, provided that the system was in, or that the laser is within the locking range of the comb. And so this is sometimes called turnkey operation as well. Anyway, well, we use this all the time now. And I'll show you a packaged up version of this a little later. Okay, so now here, coming back to the differential tuning and this Morey speed up, if you look in the upper left, there's also now a wavelength band that's been put up there. Hopefully you can see it. And then you see two versions of dark curves, okay, wavy curves. And those are measurements, okay? Those are not calculations, those are measurements on the two bands for differential tuning, okay, of the temperature, in this case, of the two resonators. And so differentially, you can see you can sweep, okay, the dispersion across the entire C band, okay, very quickly. On the other hand, if we common mode tune, there's no shifting at all. And in fact, the red and the blue in the lower left, we've offset them vertically because there's barely any tuning, okay, that goes on as a result of the temperature tuning. And so this means that you can sit at one point, okay, one wavelength, and then sweep around and actually change the dispersion. It can be normal, zero, it can be anomalous. You can also play games where pumping occurs on the upper band, and we phase match through a phonon process to the lower band. Okay, we can phase match to a phonon frequency to create a Brillouin laser. And all of that's possible, and that's what we're showing here. That middle column, the top box, is a Brillouin laser operating at a specific pump wavelength. The middle band is anomalous dispersion, that's a bright comb. The lower band is a normal dispersion, non-solitonic comb. And on the right, we're showing that you can basically pick any wavelength in C-band and run SBS, bright comb, or normal dispersion comb. And so we're calling this multimodality operation. All right, so that's one thing that's interesting about it. You might wonder, can you go to 3 rings? And you can. If we go to 3 racetracks, then the mode locking still works by pulse pair formation, but now there are more bands involved. And kind of go through this pretty quickly, but you can see these are measured bands on the upper right. And you might think, okay, there's a lot of tuning. This must be kind of complex to set up. This is what I thought when we first started doing this. It turns out it really isn't that case, or isn't that way. What we do is we'll fabricate one of these devices. There'll be some random arrangement, okay, of the dispersion. And we have a 2-step procedure. The first step involves tuning of the outer rings and to do what we call centering of the dispersion. So you can see the whole pattern is going to shift across here. So this is called centering. And so we'll have some wavelength where we'd like to kind of nominally center the dispersion. And once we've done that, then you'll have this configuration. And if you watch the upper band right now has normal dispersion, and we're going to continuously tune from normal to 0 to anomalous, okay, by now tuning the middle ring. And so what this means is that you've got, through this 2-step procedure, we can configure the device to produce, okay, a range of different types of pulses. All right, and where this has come in extremely useful is now creating broader packaged soliton microcombs. And so this is actually a packaged device. We're working with a group at JPL, and this thing is, we're taking in the direction of being miniaturized for a couple different applications. But you see the 3.5 pump, there's some micro optics here. There's a little gray disc in there, sort of a rectangular piece. That's actually phase control section. And then there's the 3-ring comb. And this is the comb spectrum that it can generate right now. And relative to the comb spectrum I showed you a little earlier, this one's already broader. And the reason this is broader is that we actually are now playing this game of tuning the dispersion, the anomalous dispersion, so that it's just slightly anomalous. These are being pumped with about 50 milliwatts of pumping power. There's now available 200, even 400 milliwatt integrated power, okay, on chips or on chip. And so we're hoping to bring those in to this kind of system. And then the comb is going to be, have much more bandwidth and be even more useful. And then finally, those dispersive waves I talked about earlier, it's probably not too surprising, but if you can move the dispersion around a lot, the comb, the soliton, will phase match, okay, at different points and start to throw coherent power into these dispersive waves. And we can use these same tuning tricks to actually tune the dispersive waves. All right. Okay, last part. Okay, now I want to connect it up with microwaves and all that background. And so this is one chart I have just to kind of remind everybody of this idea of optical frequency division and also synthesis. And so, reason combs are so incredible and so very useful is the middle panel. And combs allow us to take very, very high frequencies, like optical frequencies, and literally coherently divide them down to connect them up to electronics. And you can also start with electronics and go the other way. The electronic to optical connection is called synthesis, and that's what's shown in this sort of mechanical analogy on the upper left. And so there you've got a slow gear, and then the gear is being, taking the coherence of some quartz or maser system, and then it's transferring it to all the comb lines. And so there's 2 comb frequencies there, but in principle, there could be 100,000 comb lines. Then the upper right, mode 2, this is called division, optical frequency division, start with a very stable, could be a cold atom, could be a cavity, could be a cold lattice, take the transition, divide it down, and then read out the pulses from the comb to actually generate an electrical signal, which now has the benefit of the optical stability. And so this is the basis for now the best clocks in the world, and the optical clocks, and also the best oscillators by far. Okay, like I said, there's just no comparison between a comb-based oscillator and any kind of electrical oscillator. In the future, all oscillators will probably be comb-based. I think it's the handwriting is on the wall. Now that's what's called full OFD. All right, but in the last 10 to 12 years, there's been another style of OFD called 2-point OFD. And 2-point OFD does not require an octave comb. You need an octave span comb to actually do this sort of what we call full optical frequency division, which involves a process which has been discussed today called self-referencing. 2-point OFD is pretty simple. You need to have 2 optical lines that are very stable relative to each other, but they can be reasonably far apart spectrally. And then a comb actually connects them together and transfers their relative stability down to some detectable rate. So that's how 2-point OFD works. 2-point OFD is easy enough to implement, and there's a version of it that's commercially available now. And that's what I'm showing here. This is an actual microwave source that you can buy that's the highest performance K-band oscillator in the world, okay, both laboratory and commercial. And it uses this kind of other technique called electro-optical frequency division, which I don't have time to talk about, but it's a 2-point OFD style technique. All right. Recently, just this last year, okay, there have been now 3 reports, actually 4 reports, okay, that one of them I don't have here, but it was in Science Advances a little later than these 3, and that used this 2-point OFD technique to actually generate microwaves using microcombs. And so the idea, again, is pretty simple, and it's shown in the lower right. Find some stable cavity. So in this case, the cavity I'll show you, which is part of a team that we are members of, is a very compact Fabry-Perot cavity. Lock some lasers to a couple lines in the cavity. That produces a very nice anchor. It was an optical anchor. And then get a comb in there and read out, okay, that stability as a pulse stream made out of the comb. So there's some kind of servo control you have to implement in there. And so this is the system that we've been involved with through this large team. You can see in the upper right there, all the members of the team. And the blue panel on the left shows the optical train. The green is electronics that's being developed at Virginia. And electronics, I'm not going to talk much about it, but it's very, very nice electronics because it's preserving the very, very low phase noise tone that's created by the comb and then transferring it around. It's actually synthesizing frequencies. But in the blue, at the far left, the lasers that we're using to produce F1 and F2 in the lower right are these spiral sills. We needed to clean up DFB lasers enough to enable locking them to a very, very high Q reference cavity. The comb is a coupled ring. Okay, it's this coupled racetrack ring I've talked about. And then the reference cavity is a cavity that's being developed out of Yale. This is Peter Rackage's group in collaboration with Frank Quinlan at NIST. And it's a very impressive little cavity, not only because of its performance, but they fabricate it in parallel. They make a large number of them simultaneously and then literally dice them out, and they're flip chip bonded onto a silicon carrier. And so the whole thing can be packaged. So this is the data we had from about a year ago, actually over a year and a half ago, and this was measured at NIST. And the blue on the left, I don't know if you're familiar with phase noise data, but this is the phase noise spectral density versus offset frequency. And you can see there's this large drop, okay, many order of magnitude drop in the blue to the red. And that's when the system is locked up and performing optical frequency division. So you're getting the full benefit of the cavity, subject to the limit provided by the spectral span of the comb. And the spectral span of the comb in this case, you can see what it was in the upper right. I mentioned that we like these normal dispersion combs, these non-solitonic combs, because they have a lot of power. And so in this first demonstration, this demonstration used a non-solitonic comb. And you can see that the lines in the wings out there near the red and the blue, okay, laser references, there's a lot of power in those lines. And that's entirely because this is a normal dispersion comb. On the other hand, the span of that comb was limited to a little over 5 nanometers. And that span is really what determines how much noise reduction, okay, we're going to get in transferring the stability of the cavity down to the microsignal. So we want that span to be as large as possible. Nonetheless, at this point, this was still a nice result. It allowed the program to continue, okay, into a second phase. And but recently what we've done is we've now re-implemented the system, but using the benefit of these solitonic combs, which have broader spectral extent, but the benefit of these little peaked up dispersive waves. And those peaked up dispersive waves now give us a lot of power in a region of the comb where normally the comb line power is too weak. Okay, we couldn't do this initially. So we can tune them in and immediately picked up 10 dB. And so we're now at minus 152 dBc per hertz at 10 kilohertz offset. Okay, it's just a number. But the point is that this performance has now moved microcombs into this region of performance where they are now competing head to head, okay, with the sapphire oscillators. And so, so it's a very significant landmark. And the good news is that it's not going to end there. I mean, there's more dBs. In fact, there's at least another 10. There's probably another 20 that can be picked up with the microcombs. And so at some point, the microcombs will surpass, the sapphire oscillators, and then you'll really, have something quite impressive, a very miniature, kind of a microwave source. It could be used in a lab, and be quite robust. All right, so I'm going to stop there. I think I just reached my time point, and I want to thank all of my students. I especially want to thank the collaborators. A lot of team participation here today in this program. John Bauer, Scott Diddams, Vladimir Elchenko, Jang Lee, who's oscillator at HQ Photonics I featured today, Andre Motzko, Frank Quinlan, Peter Rackage, and Wei Zhang. And I also, of course, our sponsors. And takeaway message, which I think, everybody that works in high-Q systems, high-Q whispering gallery systems, I think this is, kind of a list we all agree to. But high-Q is super important for a lot of these new oscillator systems that we have available. for two reasons. One is you can drive them at low power, defined as power levels that are readily attainable by 3.5 lasers, but they provide incredible coherence. I didn't spend too much time on the short-term coherence of that spiral laser, but it's 40 millihertz. Okay, so I mean, it's really low. And the long-term coherence, it's improved a lot too because of the TRN noise reduction. High Q is kind of reasonably straightforward to attain today. Okay, and there's many different ways to do it. Could be Tiflin, thin film lithium niobate, nitride, and there's other systems. And then these platforms, okay, meaning those platforms that are available from foundries, we've lived for many decades with, clean rooms at universities are impressive, but, there's a certain level of control we can't maintain in a university clean room in terms of yield, fab tolerance, and so forth. It's very tricky. At least that's been our experience at Caltech. And, but now when you run through these fabs, devices come back and it's just an order of magnitude better. And so that means devices can be more complicated and there are more devices that work, okay, when a wafer comes back. And so this is kind of a different, kind of game changing in a different sort of way. And then on the microwave side, which I kind of focused on this one application today, but there's a lot of other applications. There's clocks, there are, other things that, are going on that are, very interesting and important. But the microwave side, there's a lot of attention and focus on it right now because I think the combs, this is probably one of the big areas they can provide real technology, okay, in the next probably 5 to 10 years. And so that's where I'll stop. Yeah, thanks again.
All right. Any people to start us off with questions? So that great talk. I had a question about, I was wondering if you could compare the kind of electro-optic approach to doing this 2-point
Yeah, right. Yeah.
to solitons. Like, well, why do the solitons if you can do electro-optic?
Yeah, I think the reason is that the soliton approach can give you more reduction factor. Okay, so but it's a question. It's a good question because it's one I actually ask myself a lot, and I talked to Marco, and I should probably talk to you too. But it's a question of how much more bandwidth can we pull out of modulators? Okay, EO modulators using some of the tricks that are now available. I guess I skipped through it, but I'm talking about, so essentially dispersion engineering, or essentially what I like to call Pierogi combs on a chip. Those sorts of ideas. I think Marco had that Nature paper a few years ago where it's incredibly broad electro-optic comb, and I think I don't think I particularly care how you do it. I think it would be great if there was an electro-optic comb that had let's say 4 terahertz span or 5 terahertz span. You could plug it right in and make an incredible microwave source. In fact, this company that I mentioned, they probably plug it right in. And so I think that's a very powerful technique. So I don't really have a preference there. It's just that right now, the soliton microcombs, especially with these dispersive waves, we have 5-6 terahertz span, okay, on those. So we can actually go beyond C-band. And so if EO combs could do that, EO combs would be great. And but right now, soliton combs are doing it. I think that's the only reason I can't, for this application at least. Yeah, they're lower power too. Soliton microcombs are lower power than EO combs, I think. But maybe the V-pies on EO combs can really be pressed down with the thin film lithium niobate. So it's kind of another metric, that is fun to watch and see what Hyperlight can come up with in the coming years, right? Yeah. Yeah, Steve.
I'm not sure, but I think Marco's combs are detuned. That is, the detuning is different from the resonant frequency, and they're broader when they're detuned than when they're on line center.
Yeah, that could be. I mean, this might have to do with just the physics of the way. Okay. All right. Yeah, I don't know all the details of the combs. Yeah. Okay. This is the Nature paper, essentially, maybe. Yeah. All right. Yeah. No, I think it's a great, kind of idea and approach, and I watch it a lot. Okay, been keeping tabs on it. Yep. Yeah.
Nice talk, Kerry. A couple questions actually. On when you have the soliton pairs, and you can see the two clear, spectra on the two sides. Is there any overlap spectrally? Can you generate it with zero overlap spectrally?
Oh, you mean between those two pulses?
Yeah. Do they have to interact
well,
a little bit spectrally, or can they be completely separate?
I don't know if they can be complete. You mean like just really far apart?
Yeah, and so that it's actually only the time domain part where you have an interaction.
I mean, that's okay. That's a really good question. I suspect you always have to have a little bit of overlap, because if you think about what's happening at any one frequency, it reflects the power content, okay, in each ring, okay, as a result of the hybridization. And I can tell you that there's another sort of physical argument that explains the separation a little bit, and it can kind of guide the thinking in terms of, what might drive them further apart spectrally. And that's it was actually interesting. I gave a Zoom talk to Stanford, okay, through this NTT collaboration, okay, that Yoshi runs, right? And somebody in the audience, I don't know who it was, but they asked this really good question. They said, can you think of the spectral separation between the two pulses? Is that actually or is that essentially accounting for the fact that the round trip times are different unless the group velocities are different? And so the spectral shift actually creates a little bit of group velocity change that actually, helps the pulses compensate in their propagation around. And I think that tends to be right. I haven't checked that out, but the idea is that the more you induce path length difference between the two, the larger the spectral separation would be. But I don't know how far you can push it. We've never checked that out. Yeah.
So are they connected at all by some harmonic ratio in terms of their round trips? Or, so I guess what I'm getting at is okay, let's say their path lengths were absolutely the same, the two round trips, or they kind of locked each other.
Yeah.
Then they would be the same.
Yeah.
And then you could imagine a version where obviously the way they're designed out, but you could imagine a harmonic version of it, or subharmonic version. But then you can also have the harmonic ratio where they just need to overlap, once every, I don't know, 100 round trips or something.
Yeah, I don't think that actually happens. The reason I say this is because part of this compensation, this round trip compensation that takes place, is that not only do the pulses recompress, okay, in fact, we've run simulations of this, okay, in the time domain. And what happens is that indeed one of the pulses goes around and it has a shorter round trip distance, and it gets behind, okay? And so when the pulses come together, it's slightly behind the other pulses they enter. But then the interaction not only allows them to recompress, but this pulse that's behind actually becomes ahead, right? So as they go through, they get ahead. So they're always staying synchronized, okay, if you will, because of this offset compensation, okay, that's taking place. And
so then it could be then a harmonic ratio then.
I don't know. I'd have to think about it. Yeah.
So sorry, I'm taking up all the time.
No, that's all right.
Someone else wants to talk. So instead of thinking the frequency domain, how about if you think in the time domain? Actually, for example, what Ryan Hammerly was talking earlier and Amir brought up is that you have this. You could think of it in terms of temporal trapping, in which case there's no frequency overlap, but they create a little refractive index change.
Keep going, and they just kind of pull each other together as they interact.
Through a small refractive index change.
Yeah, I know you're kind of giving me some ideas, but I'm
okay.
I'm
sorry,
sure, yeah,
because we have these ideas too. So now I got to tell the students to go back and work fast.
I haven't thought about pushing them far apart and then studying this temporal trapping, but it's an interesting idea. I have to agree. We haven't modeled it, and I have to think about it a little bit.
Okay.
It seems like there might be something there. Yeah.
And then the last question is more practical, which is, when you have the really thin silicon nitride waveguide, now everything's in the oxide. Now all of a sudden Raman can become important. And you have a lot of experience with Raman, having worked with silica and generating combs and that. Do you see the same kind of effects there, where you see appreciable Raman?
When we should be seeing, I would say we have indirect evidence that we might be seeing Raman, okay, but it's coming at the time when we also have a dispersive wave, right? And it's causing recoil, all right? And so you can look at it and say, seems like there should be some more recoil, okay, than what we're seeing as a result of the dispersive wave. We're not seeing it. So then you say, maybe there's some Raman in there offsetting, but that's kind of indirect evidence. We haven't done a systematic study like we have done in the wedge resonators of Raman. Yeah. We always have these dispersive waves in these coupled ring systems are really pronounced because you've got these little turnings that are happening, okay, in the spectrum. So they're kind of always there, right?
Probably about time for maybe one more question. I do.
This is maybe a dumb question, but when you're talking about the 2-point combs with the integrated resonator, and you're saying that these are in the long run going to outperform Sapphire. I mean, it seems like the long-term stability is basically just coming from the size of some chunk of dielectric as the flywheel. And that being the case, like, why would the kind of direct use of a Sapphire resonator be so different than using it as a?
Yeah, it's because essentially it's the relative, or so it's kind of an important point. It's a kind of good question, but the stability, all right, of the system, of an optical system, and transferring it down to the microwave comes, okay, from two things. One, it's the line widths, okay, whatever you have. So you want a high Q chunk of, quartz or whatever, right, as you said. But the other part is the span, all right? And so it's the span, okay, so you think about the relative stability, like in an Allen deviation, okay, sense, all right, is coming from the line width divided by that span. And so the more span you have, if you can capture that and divide it down, then you pull that in to the microwave. And so if you just had a piece of quartz or a sapphire that's oscillating at 10 gigahertz, all right, so like a Poseidon, okay, for example, you'd have a certain amount of stability, but you have more stability if you start with the sapphire, but with wider span, say like 5 terahertz or several terahertz. Okay, but then the relative stability of the system is several orders of magnitude greater because you've gone from 10 to say 3 to 4 terahertz. So it's that relative stability that you're transferring down, okay, that is giving you the better performance. It's not just the line width, right, of the piece of quartz or whatever it is. Yeah. So yeah.
Okay, thanks.
Yeah. Right. Yeah. Yeah. I don't know, but that's basically it. Sort of it's span and line width, right? It's the two together that give you the improvement.
I mean, is there a different, when you talk about the phase noise, like, is there a difference between the low frequency and the short term and the long term behavior?
What do you mean in terms of the performance? Yeah. So the optical systems right now do much better than the electrical system on the low offset side, and that's we have a lot of data on this. It kind of maybe it makes this argument I just made maybe more concrete, but you can see what we can do is we'll take. In fact, we've got a paper just out a few months ago where we'll take different spans, right? So you start with maybe something 10 gigahertz, 100 gigahertz, terahertz, 3 terahertz, and it's the same reference, right? So it's the same little piece of, same cavity. And you'll see at first you have a phase noise level here, and then you'll see it drops down. It drops down as the square of the division ratio, right? So if you go from, say, 2 terahertz to 20 gigahertz, that's a 100-fold reduction, 100 squared, 10 to the 4th reduction in phase noise. That's what you'll see. So you'll see 40 dB drop. And that works, okay, particularly well, okay, when you're comparing, like where quartz is at today, where sapphire is at today, when you're down, say, below a kilohertz offset frequency, because they're picking up a lot of other sources of noise. And these cavities, particularly these Fabry-Perot cavities, these vacuum cavities, or just air gap cavities, the only source of noise they have is the thermal motion of the mirrors. And so when you look at the low offset frequencies and you hit it with 40, 50 dB of OFD reduction, you have something that just hasn't existed, okay, before in terms of electronic oscillator performance. So yeah, so that low offset side is really where I think these devices shine, but they also work really well on the high offset side as well. But there you've got the servo bump and you have to work a little bit hard on moving the servo bump out. Yeah.
Okay, well, thanks. Maybe since I have the microphone, it's convenient to close the session for the day. Thanks to Kerry again.
Thank you.